Saxon Algebra 2, Lesson 85. Students, we're beginning week 23. There's just a couple more weeks before my local students take the spring midterm. And you know, if you're not a local student, I hope you'll take a midterm too. If you want to use the test that I write, just shoot me an email and I would be glad to send you a copy of the test. Local students who will be taking the test, start now preparing yourself. Make sure your formulas are memorized. Make sure that when you see a problem, you know what to look for that tells you how to do the problem, right? Don't just let it be an intuitive thing that you just look at a problem and let it like magically come to you. Know what to look for. Have specific ideas. Ask yourself as you're doing your homework, how do I know how to start this problem? That is usually the hardest part, is figuring out how to start it, okay? So what I'm suggesting is start now preparing for your homework so that when you get down here to the last few lessons, you're in good shape. You don't have to worry about extra study. I'm trying to save you time. So if you just put a little bit of extra effort into the next couple weeks, you're gonna be in great shape for that midterm without doing any extra work. Are you kidding me right now? That'd be fantastic. I want you guys to know, you don't really know me in my life outside of as a math teacher. I like to do things right, but I like to do things the easy way. I'm always trying to find ways to minimize the amount of effort I put in, but maximize the result. And I bring that to my math teaching too. I don't want you to spend extra time doing this. I know you probably have some teachers that are like, my subject is the best subject and you should spend like every minute you're alive, you should be either doing your homework for my class or thinking about it. I want you to have a life other than math, but I want you to be really good at math too. So that's all my tips and tricks and hints are designed at helping you get the most results the easiest way, right? Okay, so trust me, I'm not just trying to be a princess about this. All right, systems of nonlinear equations. Okay, remember that the word linear means line. Up until now, we've never talked about it, but all of our systems of equations have been lines. Remember, a line takes the form of y equals mx plus b, and that's cool. But what we're saying today is that there are other kinds of equations that we can put into a system and solve, and they just don't happen to be lines. So what are these other equations and what shapes do they make? That's the first question I'm going to attempt to answer for you. Have you ever been to a restaurant, is the place where I've encountered them, and gone into a walk-in fridge or a freezer, right? It's a big aluminum box with a door on it, and you walk in and the whole thing is refrigerated. I worked in a restaurant when I was in high school and college, loved it, and spent a lot of time in walk-ins. And so I'm going to invite you to a walk-in. We're gonna go into the freezer side, which is a whole room that's a freezer, don't get locked in. And inside of this freezer are some little carts with butter sculptures on them. Yes, they're butter sculptures that have been frozen. And we're going to use them. Each one of us is going to get 4 of them. But before we wheel them out of the freezer, let's go out of the freezer and stand in the hall, because I don't want to stand in this freezer anymore, we'll die. I'm going to explain to you how this sculpture was designed. Someone took a pen and applied a point to a line. This is a perfect line. It's not a pen. It ceases to be a pen. And they located the center of the line and began to pivot the line around that center. Notice how the front end and the back end of my pen are drawing circles. Now pretend that their path that they're taking, that we could draw that. This is what it would look like. there would be a circle at the top where the tip was rotating, and there would be a circle at the bottom where the bottom tip was rotating, and then the paths that my pen was making would create this shape. This is the point where I'm holding it, right? And so these are making bigger circles. This part of the pen isn't moving quite as much because it's closer to the point that I'm holding. Do you see how this looks like this? Now, imagine, just as this path, if our sculpture, this would be hollow, right? This would be like a thin side. It's just the path of the pen. So it's like a thin horn almost, a conic section. Okay, that's the name of this shape. I'm gonna write it here. Conic, as in like a cone, section. I can't explain that word. You know what it means. That's what this shape is called. And what's cool about it is that it holds within it all of the, many of the other shapes that we're gonna talk about. Here's a line, right? We already discussed that. My pen was the line that was making that path, so we could see the line right there. This is a point, okay? And there's more shapes too. Remember, this is a circle, okay? Now, here's what we're gonna do. We each have a cart in the freezer walk-in with 4 of these shapes on it made out of butter. Thin sheets of frozen butter. So let's draw all 4 of them on our paper. I'm sorry, I wish there was a place I could take you on a field trip and we could actually do this, because it would be so freaking fun when you see what we're gonna do. Mine are gonna have to get a little squishy, but that's okay. Draw 4 of them. Okay, there they are. Now, what we're going to do is we're gonna wheel them out of this freezer, and we're gonna quickly run to the dishwasher where someone has just run a load of silverware, and we're each gonna grab a handful of, we're gonna have to be careful, probably use a towel, red hot butter knives that have just come out of the dishwasher. And what we're gonna do is we're gonna slice through our butter sculptures in very specific ways to explore these different ways we can look at a conic section, all right, the different shapes we can make. So this is 3-dimensional, don't forget that. We've got our hot butter knives. For the first one, I want you to slice straight through. Let's do the top part of the cone. Then what I want you to do is take this section that you cut off and look at it. What does it look like? What it looks like, I will tell you, is, my picture's gonna be a little compromised. It's a circle, right? When we cut this off and we look at, you can look at either side, right? You can look at the bottom of the part we cut off, or you can look at this part that remains, that. But it's gonna be a circle. That kind of a slice through a conic section creates a circle. And we can write a simple formula for a circle as x squared plus y squared equals, we can just say, let's just say 6. All right? Now, before this melts, grab another one of your red hot butter knives, and this time we're not gonna cut straight through. We're gonna cut on an angle. Still through this center cut part, but we're gonna cut on an angle. When we take that off and look at it, we don't have a perfect circle. What we now have is what you used to call an oval, but guess what? I have a fancy name for it. It's called an ellipse now. Fancy math word, it just means oval, so don't let that fool you. I'm not gonna show you the formula for that one because it looks too much like a circle. So just remember, this is an ellipse, and it's just another name for an oval. Okay, great. Now, let's go to the third one. What we're gonna do with this one is we're going to cut it not within the, we're not gonna stay within the cup, we're gonna cut it at an angle. Like that. Whoa, that's kind of weird. And this shape that we're gonna get, I'll show you what it looks like. It's gonna be kind of like that. It's gonna be a U shape, right? Like that. We call this a parabola. Parabola. All right? And this last one is going to be similar to the parabola, except instead of going in an angle, we're going to cut straight down so that it cuts through the top part and the bottom part. When we pull it apart, these two sides kind of break off. We're not going to look at those. But when we look back at the main part of the sculpture, what we're going to get is an empty cup going up and an empty cup going down. This is called a hyperbola. All right, there's an equation that represents this as well. I only showed you this one. We'll get to that in a little bit more detail, all right? So really, I don't even want you to worry about that. What I want you to understand is that this basic shape, our butter sculpture, can be sliced in these 4 different ways, and it will create different shapes. These are called non-linear shapes. They're not lines, and they each have an equation, and that's called a non-linear equation. What John's going to do is he's going to give us some systems of non-linear equations that are going to be the equations of some of these different shapes, although we don't have to worry too much about that yet. I'll show you how he helps us with that. And we're going to solve the systems for x and y just like we've done in the past. So let's look at the first one. And we're gonna draw pictures of these to help us understand. So John says, solve the system. That is definitely not a line, is it? As soon as we see the squares in there, we know, whoa, that's a non-linear system. And then we have this. Oh, this looks kind of familiar, right? This just has a plane X and a plane Y. This is a linear system, right? So this, John's going to tell us, this is a circle, and this is a line. Now, I don't know exactly how these two are going to intersect, but look, this is what a system of a circle and a line could look like. We could graph a circle, and then we could have a line that goes through it, and there would be 2 points where they would intersect, right? Maybe it would just touch at 1 point, maybe at 0, but we're going to consider this kind of a picture. So we can see that our solution to this is going to have 2 pairs of points. There won't just be one place where the line and the circle intersect. There will be 2 places. So our solutions are going to be a little bit more complicated. Now, how do we solve this? Elimination, substitution, or by graphing? Well, we've graphed it a little bit and we can see, we don't even know how to graph a circle, right? Let me just start with that. We don't know how to graph circles yet, so forget about that. Elimination is not going to work because look how different our terms are, right? This is squared, this is plane, this is squared, this is plane. We're not going to be able to easily make these equations look the same so that we could eliminate down. The best approach for solving a system of nonlinear equations is substitution. So if that's your favorite, yay! You'll love it. Okay? So, how can we substitute? Well, we can see this one. I don't like these squared. I don't want to mess with them. What I would like to do is I would like to solve this equation for y first. Let's do that. I'm going to swim the y this way and the 3 this way. And then I'm going to put the y first. Y equals, it'll be 2x minus 3. Right? This, I changed this over here. That became positive, but I wrote it on the left. This, I swam across. It became a minus, and I moved that to the right. Okay, so there's my new one. Now, in order to substitute this into this, okay, so first what I did was I rearranged it. If we call this one A and this one B, we rearrange B to get this plane Y. And And now we have to square both sides so we can substitute it in there. What? So we're going to get y squared equals, and now I have to square this. It's a binomial. We got to do the dance because that's the only way to square a binomial. 4x squared minus 6x minus another 6x plus 9. So this becomes 4x squared minus 12x plus 9. I copy that up here. 4x squared minus 12x plus 9. And now, first we rearranged it. 2, we squared both sides, and I'll put 3 over here. Sub b squared into a. Lord have mercy. So at least the substitution is pretty easy because here's my y squared, here's my y squared, this is what goes in. This is all there is to it. So it's x squared plus 4x squared minus 12x plus 9 equals 9, right? This is what we're substituting in. I can put parentheses around that if I like. Okay, so let's just keep going. Let's add like terms and let's bring this over. Subtract 9. Oh, that's going to be interesting, right? So now I get 5x squared minus 12x. That cancels, equals 0. Okay. Well, how can we factor this? All we can do is take out what? An x? We can take out an x, and then we'll have 5x minus 12 equals 0. And now we know that either, I'm going to write this at the top of the next page, either x equals 0 or 5x minus 12 equals 0. All right. So now we have, to fix this, 5x equals 12. X equals 12 over 5. So now we have, I'm just going to bring this down so they're written at the same place. So now we have 2 different x values, and now we have to solve for our 2 different y values. Remember that because of the way our shapes connect, we do have 2 different versions of x and y. Let's use this, y equals 2x minus 3. We'll use that to solve for our y values. So if x equals 0, then y equals 2 times 0 minus 3, and that means y equals minus 3. So one pair of points is going to be 0 minus 3. Okay, that's one of our answers. And then over here, we'll use this equation again to solve for y if x is equal to that. So we get y equals 2 times 12 over 5 minus 3, but I'm going to change it to 15 over 5 because I'm going to have to do this multiplying, right? I saw that denominator change coming. Y equals 24 over 5 minus 15 over 5. That means y equals 9 over 5. So then our other point is 12 over 5, 9 over 5. Okay? So again, I don't have my picture on a graph, but this could be one of those points and that could be the other point. This picture might not be accurate, but you get the idea. All right, so depending on what our shapes are in our equation, we can have more than one solution, and that makes these problems a little cuckoo. And we're going to keep them simple for now, but later we're going to deal with some different shapes that will make them more complicated. All right. Now we're going to change gears and learn how to solve a different kind of system of equation that we're going to use in a problem later on. Example 85.2. All right, this will be a system of equations that solves kind of tricky, but tricky in a different way than that squaring thing we just did. These problems will be called boat in a river problems. And you'll see that there are going to be rates and times, just like we're used to. And there will be distance, right? Because we know that's a thing. Rate times time equals distance. And then we're going to have boats. And we're going to have water. Now, I'm not going to get too caught up in the explaining the way these problems work, but I just want you to understand that these are where we're getting our variables in these problems, and we'll talk more about it when we actually introduce the word part of it. Here's the way the systems will look, and John's asking us to solve this system. Okay, so this is a system of equations that John would like us to solve, and we can see this one is just begging to be eliminated, isn't it? So what we're going to do is just let this problem tell us what it wants to do. Again, the B stands for boat, and this is the time downstream. Time downstream. Okay, time downstream, these are numbers, all right? I didn't mention that, but there's a downstream and an upstream. We're not gonna worry about that yet. I just want you to know all these letters will make sense later. Right for now, we're just practicing solving. We see these two will eliminate, so let's eliminate, let's add them. We get 2 BTD equals, and we add these together and we get 40. We divide both sides by 2, and we find out that this thing called BTD equals 20. Okay, but this is two variables clumped together. It's the speed of the boat times the time. So what can we do with this? We can recognize that this matches to either one of them, but we'll use the first, right? There's a BTD in both of these. And so what we can do is plug this 20 in right up there. So now we're going to plug it in and say 20, because that's what's equal to it, plus 5TD equals 25. Subtract 20 from both sides. 5TD equals 5. So we get that the time downstream is what that stands for. You don't need to know that. Equals 1. We divide both of those by 5, right? Oh, beautiful. And now we have to solve for B. And again, we can look at this and say, okay, if b times td equals 20, then b times 1 equals 20, right? Because we know that td equals 1. And so then we get that b equals 20. Again, we're solving a system of nonlinear equations. These are not linear. They look very different from those other ones, and they have nothing to do with butter sculptures. These have to do with these Lewis and Clark type problems that, frankly, I love, and I will introduce to you. It's coming up soon. But we can solve these using this little trick, right? We get this combined variable. We get an answer that is two variables together. We'll just go back and look at your original equations, find a way to plug it in, and you can solve it. And guess what? These are the right answers. Yay. Has to do with Lewis and Clark. I love Lewis and Clark. I'm so excited by this. That's the end of lesson 85. Just the two problems. They're very different, but theoretically they're similar. But if they feel very different to you, I understand. Okay, thank you. Goodbye.